really quite small, and all the credit should go to Gordon MacDonald and the team at MacDonald Lawrence timber framing, which so I was very much a kind of stowaway in their epic task of repairing and restoring the Kinsol Trestle Bridge. But it's a real saga of enormous dimensions in every possible way, and I feel immensely lucky to have been sucked into it by my friend Gord. Anyway, Gord's in the audience, so when my memory fails me, I'm going to rely on him to fill in the blanks, which will be a good thing. And if there are any nasty hecklers, I'll pass them straight on to him as well. He'll probably be the worst of all hecklers. So the Kinsol Trestle Bridge, it spans the Coxilla River in the Cowichan Valley of Vancouver Island. Takes its name from a nearby Kinsolman copper mine, and it's 614 feet in Canadian, or 187 meters long by 145 feet or 44 meters high in the center above the gorge. It's built to a really beautiful curve as well. It was put in place by the Canadian Northern Pacific Railway. Started a line in 1911, and work on the bridge stopped during World War One, and it was completed in 1920 by the Canadian National Railways. So, and it was primarily put in there as a logging and extraction route to bring timber from the interior down to the coast. And it also developed as a passenger service and continued in use until 1979. And is it all coming through okay at your end? Yeah.
Yeah, it is, Charlie. I think a few people have still got their microphones off.
Oh, okay. No worries. No, that's fine.
Yeah, and hear you loud and clear, Charlie. I think that was just background
excellent.
waffle. Yeah.
Okay. No. You're
Everyone, please mute your microphones. Thank you.
So it in the 1950s, I suppose logging trucks and gradually took over from the steam extraction, and so by 1979 it became redundant and was taken out of service. So it was taken over by the province of British Columbia, and in 1984 was incorporated into the Trans-Canada Trail, a long-distance footpath. Its construction is really simple. The whole basis of a trestle bridge is one that you can fell the timber in the forest, square it up into 12 by 12 or 300 by 300 posts, and really quite simple frames, or bents as they're called, are fabricated, and then the railway kind of progresses with a crane, a derrick crane, which then can lower the timbers into place and span over a gorge or an opening, if you like. So the timber, it's all Douglas fir, and you'll see, I don't know, you just squint at there, you've got 12 by 12 posts, and 12 by 14 caps. These are all imperial measures, and then lots and lots of struts and whalers. So 6 by 10 struts, 3 by 10 whalers, and the jointing system is really simple. So longitudinally, the timbers are mated, just butted end on end, and a simple drift pins, couple of drift pins between each post give make the connection, and then everything else is put together with lag screws and bolts, or as we would call them, coach screws and coach bolts. So this bridge was in use until the 80s, but in 1988 there was an arson on the bridge. Someone, a bright character, built a bonfire in the center and set fire to it. It was extinguished by the forestry fire service, but nevertheless not before a great hole was pushed in the bridge. So the local government closed the bridge, took down to stop people walking across it. They removed 4 or 5 bents from each end to deny access, and then stood back and thought about how to what to do with the bridge, whether it could be repaired or. And the bridge continued to decay, I suppose, as well. It was no longer being maintained, and to most eyes, it looked quite a hairy structure as well. And the liability of the bridge sat heavily on the local government, what to do about it, how to tackle it. There was a long debate. There was a local campaign to have it restored and repaired, but after many years of sort of arguing backwards and forwards, a decision was taken finally to demolish it. And I suppose it was about this time that Gord MacDonald had returned from Britain to Vancouver Island and set up with Steve Lawrence, MacDonald and Lawrence Timber Framing. So they were a startup business, still almost working out of their bedrooms and out of shoeboxes, and horrified by the idea of this bridge being demolished. It was going to cost $1.5 million to take it down and to remove the toxic timber from the wilderness. And there was another proposal then to either build a lightweight steel bridge or a treated timber footbridge to replace the original, which would have taken the whole cost of the exercise up to about $5.7 million. And Gordon put in a proposal to repair the bridge, and argued that there'd been no proper structural assessment of survey or a conservation strategy put forward. And they sneaked out and took a look at the bridge and put in a rival proposal to repair it. So collaborating with Cascade engineers, they put a draft conservation strategy together, emphasizing the significance of the bridge, its significance in local history, especially of Vancouver Island, the fact that it was one of the largest wooden bridges in the world, the tallest timber trestle in the British Commonwealth, and this missing link in the Trans-Canada Trail. And this was kind of one last chance to save it. And they put forward these goals of the project for a conservation perspective, really, to that a full survey should be undertaken and identify all the character defining elements of it, assess the condition, and do a proper feasibility study and a cost plan. This kind of brought things to a skidding halt, and reignited interest in repairing it. Part of the local government ended up supporting them, and MacDonald Lawrence got a commission to carry out a full survey of the bridge. So that was in 2007, I believe, and so that resulted in a full report, a complete 3D set of a model of the bridge, of all 46 bents, and gave a very full insight into the nature of the problems, and fascinating insights about how accurate the accuracy of the original building was, construction was stunning. So it's all built to a very determined curve and incline as it runs round. And so the model, you can see it sort of flowing down the hillside. There's a slower incline to the north side, and to the south side it's very, very steep. Down in the base, you've got Howe truss that spans the river, which was a later repair after damage to the bridge in the 30s from a big storm. So the bridge was so after surveying the bridge, a full repair strategy was put together, a schedule of repairs, and a tender provided. So it was all set for restoration, and at that point enter the Ministry of Transportation, which was said that the bridge must satisfy all current regulations, including, because it's an earthquake zone, that it meets earthquake design regulations and codes. And on top of that, they said that even if that design was done, there's no way that they would allow the bridge to be reused with timber, aged timber, which couldn't be determined or graded, if you like. So this brought things to a bit of a skidding halt. Robin Zernolt and Cascade Engineers did a bit of lateral thinking and hit upon a solution, really, which was that when you look at this cross-section elevation of the bridge, at both ends, there were 4 or 5 bents that had been removed and dismantled and removed to allow to not allow access to the bridge, I should say. And then there were other areas which required perhaps more repair there as well. The concept had been discussed to put a lightweight steel handrail, along with various other proposals. There have been timber handrails because the original bridge had no handrailing. So there was this concept of steel handrailing, and so the proposal was put together to put these new towers, earthquake towers, if you like, 4 of them, which would be regarded as being new built. So built to the standards, and spanning between them with a lightweight steel deck. And then the idea is that in principle, in an earthquake, the original bridge could, if it were going to collapse, could collapse and fall away and would break away, leaving these new towers in place. So, and this was accepted by the regulators, and so having achieved that, then there was the engineering proved that there was massive redundancy in the bridge. It had been designed to take hundreds of tons of kinetic energy of the locomotives going across with all the timber and so on. So to take a light or even a heavy amount of foot passengers going across, and occasional maintenance vehicles, really only required a very small amount of the original structural timber. And so having done this, so basically when you look at these new bents which are waiting to go in place, it only required the outside 2 posts and the center post to perform its modern duties, if you like. So they were then able to say to the highways people, well, since we can do this, we can presumably store the original timbers within the new ones. And this was accepted as well. So everyone went away happy, and the work could then proceed. So there was a big range of logistical issues to solve. Renewing the access following the rail tracks, both ends to the north and south end of the bridge, to allow the construction traffic, setting up site offices, and also you'll see security systems so that the repaired bridge wasn't burnt down again. So there's a 24-hour camera system that's been set up there as well, and all the safety issues that would be required too. Temporary access, so footbridge formed through the Howe truss over the river, and then where one of the bents is removed, there's a scaffold has been inserted with a steel staircase to allow quick traffic from the south end of the bridge as well. So that's looking up through the scaffold, and then so there's a mixture of scaffold access, mutes, and then of course a lot of rope access. So here's some of the rope access team taking a bit of a shortcut to work across the divide there, and then mutes and craneage is brought in with an access route that was taken down through the side of the bridge. So lots of enabling works as well. Trees had grown up around the bridge, so that and so those had to be taken back to the original line of the original fire break that was along the side of the bridge. And then a very, very key strategy that was laid down by the engineers was what constituted a sound timber and what didn't. So here we've got a section of timber where it's been cut through, and you'll see a creosote coating which has penetrated in, not so deep, probably 1 inch 25 mil or so, and then a sound timber. But what were they looking in terms of what timbers would be acceptable and what weren't? And so Cascade laid down that they calculated that they basically would be happy with 2.5 inches of sound material around the exterior skin of any post. So it could be hollow in the center, but be sound on the outside and still function as a sound post. So in much the way that a high performance timber mast on a yacht wouldn't, hollow wooden mast works. The center of the timber is a kind of neutral axis in a lot of, in most cases. So you can afford to have a cavity in there. So, but what they were looking for was sound timber for 2.5 inches, whatever that is, 65 mil or so of skin, and so the rope access guys in the original survey had gone along hammering the timbers, knocking them to see whether they were sound or not, so whether they rang true. So that was that whole word of being sound, means that when you hit it, it sounds good. And so quite rapidly would detect whether a timber was sounded hollow or not, or rattled. If it was obviously poor quality, it might be rag rated as red for removal. If it was sounded good, it would probably signed off and given a green rag rating to be kept. And then anything dubious or not sure would be orange. And then so then they go back at that, check it out, either sounding more or using resistograph micro boring to check the density and to look for hollows, if you like. So these are the digital readouts of going through a poor quality one, which has got, sorry, not necessarily poor quality at all, one which is showing a hollow in the center, but with a dense skin on each side. So the hollows were sought out and surveyed, if you like. So so having done that, that then basically produced the core of the repair strategy, if you like. And then the next is the epic saga of undertaking the work. So how to get equipment in there, and in this case you'll see lowering stuff down into the gorge with a caterpillar bulldozer. So craneage, mutes, and so on were tethered and lowered down the steep slope to wherever they were needed on a regular basis, going backwards and forwards. And but then having got that kit in, then it allowed the stripping out to be done. To here you can see the top bearers being taken off and craned out of the way, which revealed the structure underneath. So pieces then that needed to be removed for repair or complete bents could be released and taken away for repair. There you can see this is the towers slots being created, if you like. So those are and component. The bents were taken to one side, all numbered up, and dismantled. A huge number of lag bolts to be removed, and bents to be repaired. So these are green rated ones being put put to one side. Some stuff was taken away to MacDonald Lawrence's workshops, where they frames could be laid out, repaired, incorporated into new bents, and so on. And then there was some upgrade of foundations as well. So here's a rock drill drilling down, and the geology was in some places is quite shattered. So they're using ground anchors to get down to solid rock and to stitch it together as well. These are the mud sills. So these are replacement mud sills. Mud sills are made in yellow cedar. So this is locally called yellow cedar. It's the it's right now, it's a Nutcasensis, is I think the Latin name for this one, and it's or yellow cypress is the other name for it. So it's a durable softwood, which was used, more durable than the Doug fir. So it's used horizontally to put the base of the bents on. So there was some upgrading on the new earthquake-proof bents. There are foundation pads put down, and then you've got the mud sills on top. And at the back, in the background there, you can see that gabions were added to hold back landslip on the steep slopes and protect the mud sills and post bases. And there's also a very clever sort of terram type matting there as well to encourage percolation of the ground and keep it drier than it originally had been. So then there was the question of the Howe truss for and how to go about repairing, conserving that. In some ways, it was one of the make or break elements of the whole repair strategy, because the bottom chords needed work on them, and unless they could be repaired in situ, it would probably kill the viability of the cost plan. Really, it was one of the major elements there. So Gord very kindly got me involved doing a consultancy to help on the survey, and to come up with, as part of the team, come up with a strategy of how to go about repairing this. These trusses, by the way, were put in 1930, between 1931 33. There'd been a massive storm which damaged a great chunk of the bridge, and so they decided that they should raise the level of the bridge. And either side, you can see these upstands in concrete that lifted it up and created a better drainage system, so it was out of danger's way. So we set about surveying, rope access surveying the bridge, going along, looking at the members in quite a lot of detail, because this is obviously a much more critical, structurally critical part. It was kind of weird experience being 45 feet above the of the water, with this moving water running through underneath you. The whole time you felt as though you were falling over. It was kind of a very, very strange and experience there really. But this is a sort of notebook going along. One of the key areas really was the connections, longitudinal connections of the bottom chord, where there were these flitched scarf joints, if you like, which had shear keys in them. So on the looking in plan section here, you've got the timbers coming along, they're butted, oops, oh, this shows it even better actually, butted together. And then flitches are placed over the outside, and then steel flitches, which have these steel keys which go into the side. And you'll see on the top side that there is beginning to be shear failure in these. So it's not exactly known as to whether it failed after use is purely due to decay, or whether that's during a high in-service loading. But nevertheless, there was a degree of failure. And then there was quite a lot of softness because you've got end grain here. So this was beginning to get quite soft. So we were resistor graphing quite carefully around these areas. And I suppose the issue then was how to repair them, and I'd like to sort of take credit for a very smart repair, but unfortunately I can't, and have to give it to the all credit should go to the original designers. And there's quite a story behind this, and I think it's when Gord was in the early days, sort of building up the work towards the repair of the bridge. They were thinking that the railway would have had massive records, kept records of maintenance and all sorts. It's quite, they're quite famous for keeping records, and was put in touch eventually with Ralph Norris, who was the retired senior engineer from the railway offices, and he went to see him and asked about the records and whether the railway still had them. And Ralph said nope. And Gord thought, oh bugger, they're gone. And Ralph sort of said, but they haven't got them because I took them. And he said, oh great, well, can I see them? Can you show them to me? And he said, nope, I've given them away. And he donated them to the local museum, and they were languishing in storage. But down there, Ralph Norris, when the railway closed down, had the one set of records that he took were of the Kinsol Trestle, and this guy looked after something like 2,500 timber bridges in Canada, and this bridge was his favorite. And when he knew that the offices were closing and that they were just going to ditch all their records and get rid of it all, he went down and rescued the all the Kinsol records, kept them at home for a long time, and eventually gave them to the local museum. And in amongst these records was it documented every repair, all the maintenance cycles, all the chemicals that they put on the bridge. Everything over its history was beautifully documented. So it was a really sweet thing. But in the drawings of the Howe truss, on one drawing, looking at the bottom chords, the designers had anticipated that these shear keyed connections would probably, over a period of time, undoubtedly fail. So they were thinking into the future, and they had already designed a beautiful plate repair, which was to extend the flitch plate beyond the rotted timber and bolt it through. So there was this. So MacDonald Lawrence appropriated this design, improved its structural engineering a bit. It lengthened the plates and took it beyond. So that's how it was repaired. And it was such a sweet thing to see the care of the original designers and engineers on the bridge and how they thought it all through. The detailing in the Howe truss itself was exquisite. The vertical tie rods that you can see were graded according to the stress that they were under. So there were different diameters of rod used, and the timbers were sized in different ways. It was beautifully done, a remarkable bit of work. Here you can see back at MacDonald Lawrence's workshops, them laying out and you get the scale of it here too, laying out these are some of the new trusses that are being built, incorporating some original timbers that could be reused. Wherever anything could be reused, it was. For the upgraded towers, then, are using split ring connectors and shear plates as well. Excuse me. Shear plates to upgrade some of the strength of the connections. There you can see the shear plate connectors and heavy duty washers as well. That's a ply spacer because in some places there are steel shoes inserted, so that's allowing for the steel to go in. And there, these are repairs, so these are columns that have been repaired with a scarf. So all that kit was put together. These are pallet boxes, and 43, 42. This is the kit for bent 43 and 42. So all its connections, all its fixings, everything would have been put into one box, transportation back to site, and then reassembling trusses, bolting them up, lots and lots of heavy duty bolts to wind up and pull into shape, and then lowering these back in from one end, working back out into the bridge. There's new bridges, new bents at the top, and then beginning to incorporate original material as well, and new base plates and mud sills. And there you begin to get the sweep of the bridge again. There's a crane working at both north and south ends. For a long time, you could only drive. You had to drive to each end. It took about an hour and a half to drive round. It took about 20 minutes to walk from the north construction site to the south. These are benches that were laid out to take craneage and so on. You can see this is in the autumn, winter, when there's a lot of water. In the summer, of course, there was a whole mitigation of fire risk to consider. But Vancouver Island is temperate rainforest. It's a very, very damp and wet atmosphere there, so working conditions are quite varied, and you've got a lot of wet in the early spring and in the autumn. And then of course the winter comes as well, where you can get dumps of snow, adding to the work issues to deal with. So by then you can see the bridge taking back into shape, all the new towers put in, and then the lightweight steel bridge. These are the caps being lowered down onto the towers. The lines beginning to be brought through, different craneage being brought, and the decking being placed into place too. You get a sense of the density of timber. It's a strange thing, because from some elevations it feels very dense and it feels lots, and then I'll show you a shot in a bit where actually you suddenly see it's a very lightweight construction as well. But when we're looking on this side, on the west elevation, which would have taken the greatest amount of weather, if you like, dominant winds are coming from that side. So the large amount of damp on that side. Whereas if you begin to look inside, you'll see that there's a lot more original timber as it goes through. And a key element in the I'm so sorry, I've been pointing in the wrong screen, so you were just seeing where my pointer was. But so I'm just saying that this is the west side, but when you look inside, you get more and more of the original timber to the east side, which is quite interesting on that front. And the other thing which was the strategy that was taken was to use untreated timber as well. So Douglas fir is moderately durable or durable softwood. The material in Vancouver Island in Canada is beautiful. It's very, very slow grown, very consistently grained, very different from our homegrown Doug fir in the UK. But so one of the things that they did was to use cobra rods, boron rods, strategically placed around all the areas which you could see where damp was concentrated, particularly by things like diagonal braces, which would take runoff, take it down and concentrate it around a bolt hole, and cause problems. So being able to predict from the original structure where the risk areas were, they then strategically drilled and placed boron rods. And this is a technique which is used a lot in North America for utility poles. It's a standard procedure to treat the base of timber utility poles for transmission lines and telephone lines with boron rods at ground level, which is where they rot, and not worry about the rest of the pole. So it's very strategic use of timber treatment, if you like. But that's looking up between some of the bends. So that's where you get this feeling of lightness. It's such they're lightweight boards which brace it so successfully, if you like. So you can see a mixture of replacement and original wailings and braces there. And here, so there's the bridge that goes back together. There were little outsets on one side of the bridge, so that maintenance people could stand aside if a locomotive was crossing the bridge, and this is replicated with these little lookouts piercing the hand railing. The hand railing is tall enough to take equestrian traffic, and to the side down below you can see this lightweight steel lattice which spans from tower to tower as well. And there it shows up in its full beauty, if you like. I think it's stunning to think that this bridge could have been destroyed. It's there are other curved ones, but I think this is possibly one of the more beautiful ones, and preserved for another 100 years or so, I think. It was such a successful project, not only in the conservation of the remarkable bridge, really, but also that the Canadian government put a major grant funding in it with big insight and foresight, really. In the early days, it wasn't long after the financial crash, and they put aside funds to help communities that were kind of suffering and marginalized, if you like. So and so this is one of the projects that they supported, and it provided employment for about 65 people for a year and a half over the period of the bridge repair. And then also there's ongoing maintenance work, regular maintenance work to be undertaken, and security of the bridge. But the other great benefit was that it transformed the economy of the communities at the railhead, so to speak, at the path ends, with the number of tourists that it's attracted in. I've been back since and visited it with Gord, and you can see here in this photo that there are lots of people walking over the bridge. People go there to get married, and you can get pony and trap visits to go out and see it, or you can trek in. And one of the times that I went out, there were, I don't know, there must have been about 200 people on the bridge at the time. So I think it's a massive feather in the hat for Gord MacDonald and Steve Lawrence, and having the balls to stand up and, without really knowing whether they could repair it or not, to put the hand up and say, right, we can repair it for less. So that brings us to the end, guys. Thank you for your time.
Fantastic, Charlie. Amazing.
Great.
Amazing.
Thank you, Charlie. You're very kind.
Wonderful presentation.
Well,
Fantastic,
it's
Charlie.
a wonderful bridge. So it's easy to present. I think the bridge does the presentation, really. You just have to
I've got